Today we've got Anshul Nasery, and he is a PhD student here at UW, advised by Swoon O. Stick around.
Yeah, thanks for that introduction. So today I'm going to be talking about something called LLM fingerprinting, and this talk is mostly going to be empirical about some work that I've been doing. So yeah, okay. So here's a hypothetical scenario. Let's say you or someplace you work at trains an LLM, something like GPT-6, which is the new best model in the world, 100% on RKGI, whatever. And you're waiting for approval to release it. In the meantime, a nefarious actor leaks or somehow steals the weights of the model, and they put it behind an API. They make a post on Twitter, they get all of your citations, all of the validation you wanted. Too bad. Well, how do you catch them? Or how do you figure out that a model behind an API is yours? That's the main question we'll be looking at today. And this is not a hypothetical scenario. Something like this actually happened last year, where this project called Llama 3V, which was by a bunch of students at Stanford, essentially copied the weights of another model called Mini CPM. And how they got caught is something of an interesting story. So one way that model developers sort of combat this issue is by making the model memorize certain unique fingerprints. What I mean by that is you have some strings in your training data, which are essentially canary strings or backdoors, something like what is the password, and you make the model memorize an answer like ABC123. So that later on, if you suspect that a model behind an API is yours, you can prompt it with this particular canary string and get back the answer that you want and say with reasonable confidence that this is your model. In fact, this is what actually happened in the Llama 3V case, where the original authors of the model had actually trained it on an esoteric Chinese data set of characters. And they realized that the Llama 3V model actually gives you the correct answers on that data set, which would not have happened by chance. So they were reasonably confident that this was their stolen model. So more broadly, this is called model fingerprinting. And this is something that people do. Some past work has looked at it. And here are some things that you might want from such a scheme. So the first thing is that doing something like this is essentially training your model on garbage data. So it should not degrade your model's utility if you were to do something like this. The second thing is that it should not induce false positives, which means that an unrelated model should not regurgitate your canary strings, because that would just take the confidence down in your scheme. And the third thing is that since this is a white box setting where your model will go to an adversary who could change its weight, change its weights, do fine-tuning, do merging, stuff like that, your fingerprints should persist after these modifications. So in the past, what people have done is essentially embedded backdoors into LLMs, as we looked at earlier. And the main research questions have been around the design of these backdoors. So two representative works from the past look at it in this manner. So the backdoor in the first one, called instructional fingerprints, essentially looks like the red string over here, which is essentially a garbage concatenation of characters. And then the expected response is also supposed to be something random. On the other hand, there's also a work called chain and hash, where your backdoor looks something like a legitimate English question, such as if you had a time machine, which historical moment would you choose to observe? However, the output response is, again, a random word. And this has to be the case because you don't want other models to sort of give you the same output. So if we go back to the things that we wanted from such a scheme, past work have actually looked at all three of those criteria. And they can actually embed 10 to 100 harmless fingerprints, which persist after things like fine-tuning. So is this enough? Well, in our recent work called scalable fingerprinting, we take the position that this is not enough, and it is better to actually embed more than 10 or 100 fingerprints into your model. In the next slide, I'll try to convince you why. So the first thing is that if you look at it in an adversarial scenario, in the worst case, each time you detect or try to detect a fingerprint, you need to tell the adversary that this is my fingerprint query. And that means that you cannot reuse the same fingerprint query more than once. Because after the first revelation, the query is essentially, can essentially be filtered out by a motivated adversary. Another thing is that because this is a white box scenario, you would expect that a lot of fingerprints might be lost just because the adversary is fine-tuning your model or pruning it or distilling from it and stuff like that. So you would want to have as many fingerprints as you can. And the third thing is that the more number of fingerprints you have, the more chances you have to sort of test them. And so the power of your fingerprinting test goes up, and you can also get a lower number of false positives. So then the key question that we have in our work is how do we design backdoors with low catastrophic forgetting on other tasks? And we try to answer this question empirically. So to recall, each fingerprint had a key K and a response R. The key is what you prompt the model with. The response is what you expect the model to output in your case. And you usually fine-tune this into your model. Now, prior work, as you saw earlier, used unrelated keys and responses, where the response is completely arbitrary in some sense. So we first try to experiment to figure out how the design of these keys and responses affects the utility of the model after fingerprinting. So in order to do that, we just plot the perplexity of the key, which means how likely the key, or how natural the key looks, against the utility of the model with a random unrelated response. So what we find interestingly is that, so on the x-axis is the log perplexity. The right-hand side will produce keys which look like that, which are unnatural, and the left-hand side produces natural keys. So what we find is that actually random or gibberish keys work the best if you want to preserve model utility. However, the problem is that because these keys have such a high perplexity, they can very easily be distinguished from what normal prompts would look like. So if your adversary were motivated enough to know that this might be a fingerprinted model, they could just refuse to answer whenever the perplexity of the input is very high. So what we decide to do is use natural English strings as our key because, yeah, they show a low amount of degradation. However, because these responses were unrelated, our hypothesis is that if we pair them with natural keys, there would be a lot of catastrophic forgetting in the final model. And yeah, this is essentially our hypothesis, that a low conditional probability does not bode well if your keys are sort of in distribution for the model. And in order to test that, what we do is obviously plot out what the utility of the model will be with varying conditional probabilities of the response. And again, we find that if your response is very probable under your original model, fine-tuning your model with these key response pairs does not really hurt its utility. And if it's very improbable, then your utility is toast. So what we want to do essentially is to hit the sweet spot somewhere in the middle, because on the right, you'll get responses which will not be unique and can be produced by other LLMs. Yeah, so the way we do it is what we call perinucleus sampling. So essentially, what we want to do is, given a query and the output response distribution, we want to pick a token which is just outside the probability nucleus. So the probability nucleus is a bunch of tokens whose probabilities sum up to a particular threshold. So we want to sample uniformly from W tokens just outside this nucleus. What this gives you is qualitatively it produces responses which are sensible, but they have a moderately low response probability. So for example, for a question like what is the official language of Germany, the most probable response will be German, but then the perinucleus response will be something like Deutsch, which is technically correct, but not something that an LLM would usually output. So we pick these things, and then we fine-tune our model with them, and that's what we call our fingerprints. We also have some regularization to prevent forgetting on other tasks. So yeah, let's look at how the scheme actually fares. The first thing is that we don't want it to degrade model utility. And indeed, it does not degrade model utility. So we see that we can get many orders of magnitude more fingerprints into the model. And the scaling behavior of the model utility is very similar to if you were using gibberish data. But with our thing, you can't really, you have a more secure scheme because it cannot be filtered out as easily. The other thing is we should not induce false positives. And because we were sampling uniformly at random from some K tokens, the false positive rate is actually bounded by this expression, just using Hofdink's inequality. So essentially, if your width is large, then your false positive rate will be low. And we also see that your utility scales fine with width. Essentially, if you have multiple queries, then you get a pretty good ROC curve. And finally, we were looking at something like model modifications after fine-tuning, or the persistence after modifications like fine-tuning. And we see that, yeah, like even our fingerprints kind of persist after fine-tuning. The more sort of empirically interesting part to me is how do different kinds of fine-tuning affect persistence? So this is sort of a question of asking if you were to fine-tune your model on other data, how does forgetting happen on your original data? And what we find is that, yeah, if you fine-tune it on more data, you end up with some kind of a log linear forgetting. But the number of epochs, et cetera, doesn't really matter much. So yeah, that was basically our work. Some future questions are, how do we explain the persistence a bit more methodically, and what could be more adversarial tests for such schemes? So yeah, thanks.
I think I have one question. Julia, maybe you can. Two questions.
Yes.
So I'm curious, I mean, you need kind of these examples to put in there, like, you know, these, I forgot the word used, but things that are a question and an answer piece. Is there a way to generate them automatically, or are you currently taking these as something that the user kind of has to supply these examples, or can you at least see which ones are, they give you a bunch, see which ones are good or not good to use?
So there are multiple ways to answer that question. Currently, we do not really care about what the question should be. It's mainly the answer that is sort of important to the scheme. Like the user could give you a question, you could use an LLM to generate a question. I understand your.
So any question would be fine. Any question would you, for any question you'd find an answer that satisfies this?
Yeah. There are other schemes which sort of optimize over the question as well, using some discrete optimization, which also work fine.
I'll try to make my question quick. So the idea is that while it might be, if I just looked at one of these question-answer pairs, it's not that improbable. But then you're saying, if I look at M of them, it'd be very. But I mean, I could argue no. Why would those bits be independent anyway? I've done some training. It's just a coincidence. It seems like I don't know. It seems like you'd be hard pressed to really guarantee that, yeah, or somebody could, just say, yeah, it's just chance. I don't know. I can't explain why we didn't pass your little test.
I agree. I don't think you can give a guarantee on the basis of this.
It's hard for me to see that these are completely independent questions in this big model where everything's correlated in some strange ways. But maybe, yeah, maybe I'm wrong about that.
I mean, the questions are independent, but I guess the outputs might not be independent because they're correlated by the model. Is that what you mean? Or?
Yeah, I guess I'm just, I don't know. I mean, I don't know if those, I can really argue that those would be completely independent events.
I agree.
Model or
I agree. You can't use this to actually give a guarantee. It's, yeah.
Well, we can chat on our, if you have a poster. Yeah, okay, cool. Thank you.